Why planes can't fly faster than 600 miles per hour. At nearly 600 miles per hour, a passenger jet is already doing something that still feels almost unreal. It is outrunning weather systems, leaping across continents in a single afternoon, and moving so fast that towns, rivers, highways, and fields below seem to drift past like a slow-motion map. From inside the cabin, it feels calm. A cup of coffee barely shakes. A passenger opens a window shade and sees clouds glowing in silence. But push that same aircraft just a little faster, and the invisible air around it begins to push back. Not softly, not politely, violently. The strange truth is that modern airliners are not held back because engineers ran out of power. They are held back by a wall made of shock waves, fuel burn, noise, heat, money, and history. The story begins in the earliest days of powered flight, when speed was not measured in hundreds of miles per hour, but in nerve, patience, and survival. In 1903, the Wright brothers lifted a fragile machine off the sand at Kitty Hawk, and that first flight moved slower than a car rolling through a quiet neighborhood. It was not sleek, it was not comfortable, it was barely controllable. The great problem of the age was not how to fly faster. The great problem was how to stay in the air at all. Early airplanes were built from wood, fabric, wires, and hope. Their wings were thick and simple. Their engines were weak, noisy, and unreliable. Their pilots sat exposed in open cockpits with cold wind tearing at their faces, oil mist sticking to their goggles, and almost nothing between their bodies and the sky. Every flight felt physical. Every gust mattered. Speed came slowly, piece by piece, through trial, accident, and invention. Stronger engines, cleaner shapes, better propellers, metal frames, enclosed cabins. Each improvement made airplanes a little less fragile and a little more believable. By the 1920s and 1930s, aircraft had become faster, stronger, and far more useful. Mailplanes crossed dangerous routes in darkness and bad weather. Military aircraft pushed designers towards sleeker bodies and more powerful engines. Passenger aircraft began to look less like flying kites and more like machines built for real distance. But they were still propeller-driven, and propellers had their own hidden ceiling. As the tips of propeller blades approached the speed of sound, they became loud, inefficient, and harder to control. Long before the entire airplane reached sonic speed, parts of it were already crashing into the strange physics of compressible air. Then came war, and war changed everything. During World War II, aircraft development accelerated with frightening urgency. Fighters had to climb higher, turn harder, dive faster, and survive longer. Bombers had to carry heavier loads across greater distances while crews sat in freezing, vibrating metal shells high above enemy territory. Engineers began to discover that as aircraft approached very high speeds, the air no longer behaved like a smooth, obedient stream. It compressed. It bunched up. It piled against the wings. It formed shock waves. Controls stiffened. Drag rose sharply. Some aircraft were pulled into terrifying high-speed dives that pilots could barely escape. This was the mysterious region called transonic flight, the uneasy zone near the speed of sound. It was not completely subsonic, but not safely supersonic either. It was a strange borderland where parts of the air flowing over the wings could move faster than sound even while the airplane itself remained below that speed. That meant an aircraft did not need to fully break the sound barrier to suffer from shock waves. It only needed to get close enough for the air to change character. The breakthrough came with new shapes. Swept wings helped delay the formation of shock waves. Thinner airfoils reduced drag. Jet engines removed the propeller problem entirely and opened the door to a different kind of speed. Wind tunnels became laboratories for survival, where invisible forces were studied before they could destroy real airplanes. In 1947, Chuck Yeager flew the Bell X-1 through the sound barrier, proving that controlled supersonic flight was possible, but the machine that did it was not a passenger airplane. It was a rocket-powered experimental aircraft carried into the sky by a bomber built for one purpose: to cross a boundary that had frightened pilots for years. The jet age arrived soon after, and for a brief moment it seemed as if passenger planes might simply keep getting faster forever. Early jetliners such as the de Havilland Comet and later the Boeing 707 turned long-distance travel into something modern, glamorous, and almost cinematic. airports filled with polished metal aircraft. Passengers dressed as if stepping onto an airplane was an event. Families waved from observation decks. The world began to shrink, not slowly, but in great silver leaps. But as airlines learned to operate jets every day in real weather with real passengers, real schedules, and real costs, a hard truth appeared. Speed was expensive. A passenger jet could be designed to fly faster than 600 miles per hour, but the price of doing so grew dramatically near the speed of sound, around Mach 0.8 to Mach 0.85. Depending on altitude and design, the air moving over the wings begins to form local supersonic pockets. Shockwaves appear. Drag rises. The engines must burn much more fuel just to gain a little extra speed. The airplane may arrive a few minutes earlier, but the airline pays heavily for every one of those minutes. This is why modern airliners settled into a narrow sweet spot. Most cruise around 500 to 575 miles per hour, depending on wind, altitude, weight, and aircraft type. That is fast enough to carry passengers across oceans, countries, and time zones with astonishing efficiency, but not so fast that the airplane spends the entire flight fighting transonic drag. The limit is not a simple red line painted across the sky. It is a balance point found through decades of engineering, economics, and hard experience. The transformation era reached its most dramatic chapter with Concorde. In the 1960s, Britain and France joined forces to build a passenger aircraft that would not merely approach the sound barrier, but smash through it and keep going. Concorde was thin, elegant, and futuristic, with a needle-like nose, sharp delta wings, and engines that sounded closer to military power than ordinary transportation. It could fly at more than twice the speed of sound. London to New York could take less than 4 hours. For passengers aboard, the sun could seem to hang in the wrong place or even move backward across the sky. But Concorde revealed the true price of speed. It burned enormous amounts of fuel. It carried far fewer passengers than a wide-body jet. Its sonic boom was so loud that supersonic flight over land became heavily restricted. Its skin heated up during flight as it pushed through the air faster than sound. Its maintenance was expensive, its routes were limited. It became an icon, a symbol of futuristic travel, but not a mass transportation solution. While ordinary airliners grew larger, quieter, safer, and more fuel-efficient, Concorde remained a magnificent exception. Its failure as a mainstream aircraft shaped the modern sky more than its success ever could. Airlines learned that most passengers cared more about ticket price, safety, range, comfort, reliability, and schedule than cutting a few hours from a route at enormous cost. Aircraft manufacturers followed the money and the physics. The future of aviation did not become pure speed. It became efficiency. It became range. It became quieter cabins, lower fuel burn, better engines, and aircraft that could fly profitable routes day after day. That is why the modern airliner looks the way it does. A Boeing 787, Airbus A350, or modern 737 is not shaped like a bullet because it is not trying to be one. Its wings are carefully curved to create lift while keeping drag under control. Its engines are large because high bypass turbofans move huge amounts of air efficiently, not because they are built for a supersonic sprint. Its winglets reduce swirling vortices at the tips. Its body is long and smooth but still wide enough to hold passengers, cargo, fuel, wiring, insulation, luggage bins, galleys, bathrooms, emergency equipment, and all the hidden systems that make ordinary air travel possible. Every part is a compromise. Go faster, and the wing may need to become thinner and more sharply swept, but that can make takeoff and landing more difficult. Go faster, and the engines may need a very different design, but that can make them louder, hotter, and much thirstier. Go faster, and the structure may need to handle more heating, pressure, vibration, and stress, but that adds weight. Add weight, and the aircraft needs more lift, more fuel, more runway, and more money to do the same job. So the 600-mile-per-hour idea is not really a hard impossibility. It is a practical ceiling for ordinary passenger aviation. Some airliners can briefly exceed it relative to the ground with strong tailwinds. Some aircraft have maximum speeds near or above that range in true airspeed. But routine flight is different from proving what is technically possible. Airlines do not operate at the edge unless the edge pays back. Near 600 miles per hour, the edge usually sends the bill. The unexpected twist is that some passenger jets have already gone faster than sound over the ground without being supersonic through the air. With a powerful jet stream pushing from behind, an aircraft can show a ground speed above 700 miles per hour, while the air flowing around its wings remains safely subsonic. To the passengers, nothing feels unusual. No boom, no shaking, no dramatic announcement. The aircraft is simply riding a fast-moving river of air, like a boat carried by a powerful current. So planes do not settle around 600 miles per hour because humans reach the limit of imagination. They settle there because history tested the alternatives. Propellers met compressibility. Fighters discovered shockwaves. Jetliners found the economic sweet spot. Concorde proved that speed could be conquered, but not cheaply. The modern airliner is the result of all those lessons. Not the fastest aircraft possible, but the fastest aircraft that can safely, quietly, efficiently, and repeatedly carry millions of people across the world.